A CubeSat is a type of miniaturized satellite for space research made up of multiples of 10A, 11.35 centimeters cubic units, has a mass of no more than 1.33 kilograms per unit, and often see the use of commercial off-the-shelf components for its electronics and structure. CubeSats are most commonly put in orbit by deployers on the International Space Station, or launched as secondary payloads on a launch vehicle. Beginning in 1999, California Polytechnic State University and Stanford University developed the CubeSat specifications to promote and develop the skills necessary for the design, manufacturing, and testing of small satellites intended for low Earth orbit that perform a number of scientific research and explore new space technologies. Academia accounted for the majority of CubeSat launches until 2013, when over half of launches were for non-academic purposes, and by 2014 most newly deployed CubeSats were for a commercial or amateur project. CubeSats have been built by large and small companies alike, while other projects have been the subject of Kickstarter campaigns. Uses typically involve experiments which can be miniaturized or serve purposes such as Earth observation or amateur radio. Many CubeSats are used to demonstrate spacecraft technologies that are targeted for use in small satellites or that present questionable feasibility and are unlikely to justify the cost of a larger satellite. Scientific experiments with questionable underlying theory may also find themselves aboard CubeSats as their low cost could justify riskier experiments. Biological research payloads have been flown on several missions, with more planned. Several missions to the Moon and Mars are planning to use CubeSats. History. The CubeSat reference design was proposed in 1999 by Professors Jordi Puig-Suari of California Polytechnic State University and Bob Twiggs of Stanford University. The goal was to enable graduate students to be able to design, build, test and operate in space a spacecraft with capabilities similar to that of the first spacecraft, Sputnik. The CubeSat as initially proposed did not set out to become a standard. Rather, it became a standard over time by a process of emergence. The first CubeSats were launched in June 2003 on a Russian Irkut, and approximately 75 CubeSats had been placed into orbit by 2012. The need for such a small factor satellite became apparent in 1998 as a result of work done at Stanford University's Space System Development Laboratory. At SSDL, students had been working on the Opal microsatellite since 1995. Opal's mission to deploy daughter-ship picosatellites had resulted in the development of a launcher system that was hopelessly complicated, and could only be made to work most of the time. With the project's delays mounting, Twiggs sought out DARPA funding that resulted in the redesign of the launching mechanism into a simple pusher-plate concept with the satellites held in place by a spring-loaded door. Desiring to shorten the development cycle experienced on Opal and inspired by the picosatellites Opal carried, Twiggs set out to find, how much could you reduce the size and still have a practical satellite? The picosatellites on Opal were 10.1A, 7.6A, 2.5 centimeters, a size that was not conducive to covering all sides of the spacecraft with solar cells. Inspired by a 4-inch cubic plastic box used to display Beanie Babies in stores, Twiggs first settled on the larger 10-centimeter cube as a guideline for the new CubeSat concept. A model of a launcher was developed for the new satellite using the same pusher plate concept that had been used in the modified Opal launcher. Twiggs presented the idea to Puig-Suari in the summer of 1999 and then at the Japan-US Science, Technology, and Space Applications Program Conference in November 1999. The term CubeSat was coined to denote nanosatellites that adhere to the standards described in the CubeSat design specification. Cal Poly published the standard in an effort led by aerospace engineering professor Jordi Puig-Suari. Bob Twiggs, of the Department of Aeronautics and Astronautics at Stanford University, and currently a member of the Space Science faculty at Morehead State University in Kentucky, has contributed to the CubeSat community. His efforts have focused on CubeSats from educational institutions. The specification does not apply to other cube-like nanosatellites such as the NASA MEPSI nanosatellite, which is slightly larger than a CubeSat. Design: the CubeSat specification accomplishes several high-level goals. The main reason for miniaturizing satellites is to reduce the cost of deployment and are often suitable for launch in multiples, using the excess capacity of larger launch vehicles. The CubeSat design specifically minimizes risk to the rest of the launch vehicle and payloads. Encapsulation of the launch area payload interface takes away the amount of work that would previously be required for mating a piggyback satellite with its launcher. Unification among payloads and launchers enables quick exchanges of payloads and utilization of launch opportunities on short notice. Standard CubeSats are made up of 10A, 11.35 cm units designed to provide 10 cm or 1 liter of useful volume while weighing no more than 1.33 kg per unit. The smallest standard size is 1U and 3U is the largest, which does not occupy allowed extra volumes. The Aerospace Corporation has constructed and launched 2 smaller form CubeSats of 0.5U for radiation measurement and technological demonstration. In recent years, larger CubeSat platforms have been proposed, most commonly 6U and 12U, to extend the capabilities of CubeSats beyond academic and technology validation applications and into more complex science and national defense goals. In 2014, 2 6U Perseus M CubeSats were launched for maritime surveillance. Those 2 CubeSats represent the largest CubeSats flown as of 2015. Since nearly all CubeSats are all 10A, 10 cm, they can all be launched and deployed using a common deployment system called a Polypico satellite orbital deployer, developed and built by CalPoly. No electronics form factors or communications protocols are specified or required by the CubeSat design specification, but COTS hardware has consistently utilized certain features which many treat as standards in CubeSat electronics. Most COTS and custom-designed electronics fit the form of PC/104, which was not designed for CubeSats but presents a 96 mm profile that allows most of the spacecraft to unregistered trademark S volume to be occupied. Technically, the PCI-104 form is the variant of PC/104 used, and the actual pinout used does not reflect the pinout specified in the PCI-104 standard. Stack-through connectors on the boards allow for simple assembly and electrical interfacing, and most manufacturers of CubeSat electronics hardware hold to the same signal arrangement, but some products do not, and care must be taken to ensure consistent signal and power arrangements to prevent damage. Different classifications are used to categorize such miniature satellites based on mass. 1U CubeSats belong to the genre of picosatellites. Minisatellite, microsatellite, nanosatellite, picosatellite, femtosatellite. Most CubeSats carry 1 or 2 scientific instruments as their primary mission payload. Structure equals, the number of volumes classifies the size of CubeSats, and according to the CubeSat design specification and are scalable along only one axis to fit the forms of 0.5U, 1U, 1.5U, 2U, or 3U. All the standard sizes of CubeSat have been built and launched, and represent the form factors for nearly all launched CubeSats as of 2015. Materials used in the structure must feature the same coefficient of thermal expansion as the deployer to prevent jamming. Specifically allowed materials are 4 aluminum alloys, 7075, 6061, 5005, and 5052. Aluminum used on the structure which contacts the PPOD must be anodized to prevent cold welding, and other materials may be used for the structure if a waiver is obtained. Protrusions beyond the maximum dimensions are allowed by the standard specification, to a maximum of 6.5 mm beyond each side. Any protrusions may not interfere with the deployment rails and are typically occupied by antennas and solar panels. In revision 13 of the CubeSat design specification, an extra available volume was defined for use on 3U projects. The additional volume is made possible by space typically wasted in the PPOD Mk. 3 spring mechanism. 3U CubeSats which utilize the spacer designated 3U+ and may place components in a cylindrical volume centered on one end of the CubeSat. The cylindrical space has a maximum diameter of 6.4 cm and a height no greater than 3.6 cm while not allowing for any increase in mass beyond the 3U's maximum of 4 kg. Propulsion systems and antennas are the most common components that might require the additional volume, though the payload sometimes extends into this volume. Deviations from the dimension and mass requirements can be waived following application in negotiation with the launch service provider. Attitude control equals. Attitude determination and control for CubeSats relies on miniaturizing technology without significant performance degradation. Tumbling typically occurs as soon as a CubeSat is deployed, due to asymmetric deployment forces and bumping with other CubeSats. Some CubeSats operate normally while tumbling, but those that require pointing in a certain direction or cannot operate safely while spinning must be detumbled. Systems that perform attitude determination and control include reaction wheels, manticores, thrusters, star trackers, sun sensors, earth sensors, angular rate sensors, and GPS receivers and antennas. Combinations of these systems are typically seen in order to take each method's advantages and mitigate their shortcomings. Reaction wheels are commonly utilized for their ability to impart relatively large moments for any given energy input, but reaction wheels' utility is limited due to saturation, the point at which a wheel cannot spin faster. Examples of CubeSat reaction wheels include the Maryland Aerospace MAI-101 and the Sinclair Interplanetary RW0.03-4. Reaction wheels can be desaturated with the use of thrusters or manticores. Thrusters can provide large moments by imparting a couple on the spacecraft, but inefficiencies in small propulsion systems cause thrusters to run out of fuel rapidly. Commonly found on nearly all CubeSats are manticores which run electricity through a solenoid to take advantage of the Earth's magnetic field to produce a momentum. ADCS modules and solar panels typically feature built-in manticores. For CubeSats that only need to detumble, no attitude determination method beyond an angular rate sensor or electronic gyroscope is necessary. Pointing in a specific direction is necessary for Earth observation, orbital maneuvers, maximizing solar power, and some scientific instruments. Directional pointing accuracy can be achieved by sensing the Earth and its horizon, the Sun, or specific stars. Sinclair Interplanetary's SS-411 Sun Sensor and Street 16 Star Tracker both have applications for CubeSats and have flight heritage. Pumpkin's Colony I bus uses an aerodynamic wing for passive attitude stabilization. Determination of a CubeSat's location can be done through the use of onboard GPS, which is relatively expensive for a CubeSat, or by relaying radar tracking data to the craft from Earth-based tracking systems. Propulsion CubeSat propulsion has made rapid advancements in the following technologies: cold gas, chemical propulsion, electric propulsion, and solar sails. The biggest challenge with CubeSat propulsion is preventing risk to the primary payload while still providing significant capability. Most propulsion systems require pressurized tanks or hazardous propellants. The CubeSat design specification requires a waiver to deviate from general requirement limiting propulsion systems to the following: less than 1.33 kg mass for 1U, up to 4.0 kg mass for 3U, pressurization less than 1.2 standard atmospheres, less than 100 Wh of stored chemical energy, and no hazardous materials. Cold gas thrusters. A cold gas thruster uses a typically inert gas as the reaction mass, and usually consists of a pressurized tank, a valve to control its release and a nozzle, and plumbing connecting them. Examples of CubeSat cold gas thrusters are VACCO's PUC, and Moog's 58E143. Cold gas propulsion systems are very safe since the gases used do not have to be volatile or corrosive, which is highly advantageous to CubeSats which are often restricted from hazardous materials. Unfortunately, only low performance can be achieved with them, preventing high impulse maneuvers even in low-mass CubeSats. Chemical propulsion Chemical propulsion systems use a chemical reaction to produce a high-pressure, high-temperature gas that accelerates out of a nozzle. Chemical propellant can be liquid, solid or a hybrid of both. Liquid propellants can be a monopropellant passed through a catalyst, or bipropellant. The benefits of monopropellants are relatively low complexity, high thrust output, low power requirements, and high reliability. Examples of chemical propulsion for CubeSats include Experiment Propulsion Labs AM motor, Aerojet's MPS-120 hydrazine thruster, and BizX's green monopropellant thruster. Another example is hydrogen propulsion by on-orbit electrolysis of water. Electric propulsion. Electric propulsion uses electromagnetics or electrostatics to expel propellant at high speed. Electric thrusters typically use much less propellant than chemical rockets because they have a higher exhaust speed than chemical rockets, and can enable interplanetary travel for CubeSats. Examples of electric propulsion include Hall effect thrusters, ion thrusters, electrospray thrusters, and pulsed plasma thrusters. A student-led project at Duke University proposes to use electrospray propulsion to propel a CubeSat to Mars, and NASA's Lunar IceCube proposes to use the BizX BIT-3 ion thruster to achieve lunar orbit. Solar sail. Solar sails are a form of spacecraft propulsion using the radiation pressure from stars to push large ultra-thin mirrors to high speeds, requiring no propellant. Several CubeSats employ a solar sail as its main propulsion and stability in deep space, including the 3U nanosail D2 launched in 2010, the Light Sail 1 scheduled for launch in April 2016, and the proposed Near-Earth Asteroid Scout. The EastCube 1 used an electric solar wind sail. Power equals. CubeSats use solar cells to convert solar light to electricity that is then stored in rechargeable lithium-ion batteries that provide power during eclipse as well as during peak load times. These satellites have a limited surface area on their external walls for solar cells assembly, and has to be effectively shared with other parts, such as antennas, optical sensors, camera lens, propulsion systems, and access port. Lithium-ion batteries feature high energy-to-mass ratios, making them well-suited to use on mass-restricted spacecraft. Battery charging and discharging is typically handled by a dedicated electrical power system. Batteries sometimes feature heaters to prevent the battery from reaching dangerously low temperatures which might cause battery and mission failure. Missions with higher power requirements can make use of attitude control to ensure the solar panels remain in their most effective orientation toward the Sun, and further power needs can be met through the addition and orientation of deployed solar arrays. Recent innovations include additional spring-loaded solar arrays that deploy as soon as the satellite is released, as well as arrays that feature thermal knife mechanisms that would deploy the panels when commanded. CubeSats may not be powered between launch and deployment, and must feature a remove before flight pin which cuts all power to prevent operation during loading into the P-pod. Additionally, a deployment switch is actuated while the craft is loaded into a P-pod, cutting power to the spacecraft, and is deactivated after exiting the P-pod. Telecommunications equals. The low cost of CubeSats has enabled unprecedented access to space for smaller institutions and organizations, but, for most CubeSat forms, the range and available power is limited to about 2 W for its communications antennae. They can use radio communication systems in the VHF, UHF, L, S, C and X band. For UHF-VHF transmissions, a single helical antenna or 4 monopole antennae are deployed by a spring-loaded mechanism. Because of tumbling and low power range, radio communications are a challenge. Many CubeSats use an omnidirectional monopole or dipole antenna built with commercial measuring tape. For more demanding needs, some companies offer high-gain antennae for CubeSats, but their deployment and pointing systems are significantly more complex. For example, MIT and JPL are developing an inflatable dish antenna with a useful range to the Moon. Costs equals. CubeSat forms a cost-effective independent means of getting a payload into orbit. With their relatively small size, one new CubeSats could each be made and launched to low Earth orbit for an estimated cost of $65,000 to $80,000. After delays from low-cost launches such as interorbital systems, by 2015 launch prices have been about $100,000 per unit, plus less than $50,000 to construct a basic 1U CubeSat. This price tag, far lower than most satellite launches, has made CubeSat a viable option for schools and dozens of universities and some companies around the world to develop their own CubeSats. Some CubeSats have complicated components or instruments, such as LightSail 1, which pushes their construction cost into the millions. Notable past missions. One of the earliest CubeSat launches was on June 30, 2003 from Plesetsk, Russia, with ERCOT Launch Services' multiple orbit mission. CubeSats were put into a sun-synchronous orbit and included the Danish AAU CubeSat and DTUSAT, the Japanese 11-4 on Qt-1, the Canadian Connex-1, and USA's QuakeSat. On February 13, 2012, 3 PPODs deployers containing 7 CubeSats were placed into orbit along with the LERIS satellite aboard an Avio Vega rocket launched from French Guiana. The CubeSats launched were EST-ATR, Goliath, Massat-1, PWSat, Robusta, UniCubeSat GG, and XATCOBEO. On September 13, 2012, 11 CubeSats were launched from 8 PPODs, as part of the OutSat secondary payload aboard a United Launch Alliance Atlas V rocket. This was the largest number of CubeSats successfully placed to orbit on a single launch. This was made possible by use of the new NPS CubeSat launcher system developed at the Naval Postgraduate School. The following CubeSats were placed in orbit: SMDC-1 2.2, SMDC-1 2.1, AeroCube 4.0, X3, Aeneas, CSSWE, CP5, CXBN, Cinema, and Re. 5 CubeSats were placed into orbit from the International Space Station on October 4, 2012, as a technology demonstration of small satellite deployment from the ISS. They were launched and delivered to ISS as a cargo of Counetary 3, and an ISS astronaut prepared the deployment mechanism attached to Japanese experiment module's robotic arm. 4 CubeSats were deployed from the Cygnus Mass Simulator, which was launched April 21, 2013 on the maiden flight of Orbital Sciences' Antares rocket. 3 of them are 1U phone SATs built by NASA's Ames Research Center to demonstrate the use of smartphones as avionics in CubeSats. The 4th was a 3U satellite, called Dove-1, built by Planet Labs. The working principles of the theoretical electric solar wind sail propulsion underwent successful testing in May 7, 2013 with the EstCube-1, developed as part of the Estonian student satellite program. During the EstCube-1 flight, 10 meters of 20 Euro 50 micrometer thick E-sail wire were deployed from the satellite to affect the attitude control. To control the E-sail element's interaction with both the plasma surrounding the Earth and the effect it has on the spacecraft's spinning speed, the students adapted 2 miniaturized electron emitters connected to the E-sail element, which it loads positively to 500 volts by shooting out electrons. The positive ions in the plasma push the E-sail element and influence the satellite's rotation speed. A total of 33 CubeSats were deployed from the ISS on February 11, 2014. Of those 33, 28 were part of the Flock 1 constellation of Earth imaging CubeSats. Of the other 5, 2 are from other US-based companies, 2 from Lithuania, and 1 from Peru. The LightSail A is a 3U CubeSat prototype propelled by a solar sail. It was launched on May 20, 2015 from Florida. Its 4 sails are made of very thin mylar and have a total area of 32 m2. This test will allow a full checkout of the satellite systems in advance of the main 2016 mission. Future projects: an ambitious problem is the CubeE50, an international network of 50 CubeSats for multi-point, in situ measurements in the lower thermosphere and re-entry research. CubeE50 is an initiative of the von Karman Institute and is funded by the European Union. WNet CubeSats are foreseen, with one unit providing the usual satellite functions and the other unit accommodating a set of standardized sensors for low thermosphere and re-entry research. 35 CubeSats are envisaged to be provided by universities in 19 European countries, 10 by universities in the US, 2 by universities in Canada, 3 by Japanese universities, 1 by an institute in Brazil, and others. 10 2U or 3U CubeSats are foreseen to serve for in-orbit technology demonstration of new space technologies. All 50 CubeSats will be launched together on a single Cyclone 4 launch vehicle in February 2016. The request for proposals for the QB50 CubeSat was released on February 15, 2012. 2016 InSight mission, Marco CubeSats the 2016 launch of the InSight stationary lander to Mars, will include 2 CubeSats to fly by Mars to provide additional relay communications from InSight to Earth during entry and landing. This will be the first flight of CubeSats in deep space. The mission CubeSat technology is called Mars Cube 1, a 6-unit CubeSat, 14.4 inches by 9.5 inches by 4.6 inches. Marco is an experiment, but not necessary for the InSight mission, to add relay communications to space missions in important time durations, in this landing from the time of InSight atmospheric entry and landing. Marco will launch in March 2016 from Vandenberg Air Force Base, California on the same Atlas V rocket as the InSight lander. The 2 CubeSats will separate from the Atlas V booster after launch and then travel in their own trajectories to Mars. After separation, Marco will deploy 2 radio antennas and 2 solar panels. The high-gain, X-band antenna is a flat panel to direct radio waves. Marco will navigate to Mars independently from the InSight lander, making their own course adjustments on the flight. Marco will fly by Mars while InSight is landing in September 2016. During InSight's planned entry, descent and landing in September 2016, the lander will transmit information in the UHF radio band to NASA's Mars Reconnaissance Orbiter flying overhead. MRO will forward EDL information to Earth using a radio frequency in the X band, but cannot simultaneously receive information in one band if transmitting on another. Confirmation of a successful landing could be received on Earth several hours after, so Marco would be a technology demonstration of real-time telemetry during the landing. CubeSat Launch Initiative NASA created in 2010 the CubeSat Launch Initiative that aims to provide access to space for CubeSats developed by educational institutions and non-profit organizations. Selected experiments fly as auxiliary payloads on NASA rocket launches or are deployed from the International Space Station. Launch and deployment. Unlike full-sized spacecraft, CubeSats have the ability to be delivered into space as cargo and then deployed by the International Space Station. This presents an alternative method of achieving orbit apart from launch and deployment by a launch vehicle. NanoRacks and Made in Space are developing means of constructing CubeSats on the International Space Station. Launch systems NASA has launched more than 30 CubeSats over the last several years, and as of 2015, it has a backlog of more than 50 awaiting launch. No matter how inexpensive or versatile CubeSats may be, they must hitch rides as secondary payload on large rockets launching much larger spacecraft, at prices starting around $100,000. SpaceX and Japan Manned Space Systems Corporation are 2 recent companies that offer commercial launch services for CubeSats as secondary payload, but a launch backlog still exists. Meanwhile, India's ISRO has been commercially launching foreign CubeSats since 2009 as secondary payloads. Very few companies and research institutes offer regular launch opportunities in clusters of several cubes. ISC Cosmetras and Eurocot are 2 companies that offer such services. On May 5, 2015, NASA announced a program based at the Kennedy Space Center dedicated to develop a new class of rockets designed specifically to launch very small satellites, the NASA Venture Class Launch Services, which will offer a payload mass of 30 kilograms to 60 kilograms for each launcher. 5 months later, in October 2015, NASA awarded a total of $17.1 million to 3 separate startup launch companies for one flight each, $6.9 million to Rocket Lab, $5.5 million to Firefly Space Systems, and $4.7 million to Virgin Galactic. The payloads for the 3 flights under the VCLS contract have not yet been assigned. Deployment PPODs were designed with CubeSats to provide a common platform for secondary payloads. PPODs are mounted to a launch vehicle and carry CubeSats into orbit and deploy them once the proper signal is received from the launch vehicle. The PPOD Mk3 has capacity for 3 1U CubeSats, or other 0.5U, 1U, 1.5U, 2U, or 3U CubeSats combination. Up to a maximum volume of 3U other CubeSat deployers exist, with the NanoRacks CubeSat deployer on the International Space Station being the most popular method of CubeSat deployment as of 2014. Some CubeSat deployers are created by companies, such as the ICEPod or SPL, while some have been created by governments or other non-profit institutions such as the XPod, TPOD, or the JSSOD on the International Space Station. While the PPOD is limited to launching a 3U CubeSat at most, the NRCSD can launch a 6U CubeSat and the ICEPod can launch a different form of 6U CubeSat. Cascio was deployed by hand during a spacewalk on the International Space Station in 2014. See also, AMSAT, Canadian Advanced Nanospace Experiment Program, CubeSat Space Protocol, Israeli Nanosatellite Association, Nanosatellite Launch System, OSCA, Lunar IceCube. References. External links, CubeSat Introduction, 2-minute video, Geospace. CubeSat program official website contains information about upcoming launches. AMSAT's list of CubeSats generally kept well up to date.